If I were to shoot a bunch of paintballs through those slits over there, you'd probably expect to see 2 columns of paint with a little bit of splattering on the sides, right? And you'd probably expect to see the same sort of pattern no matter how small the bullets I fired were, right? Wrong. If these paintballs were the size of electrons, you'd see something a little bit more like this. Let's imagine the paintballs are electrons, and those slits are each about as wide as a single atom. If we shoot our electrons through, they wouldn't create 2 columns, they'd create a series of columns. Scientists have done just that, and they found the same to be true of other fundamental particles, like protons and neutrons. When they tried to figure out why, they realized that the patterns created by these particles look like the patterns created by waves. As these water waves pass through these 2 slits, they diffract and interfere with one another. Where 2 peaks or 2 troughs line up, we find constructive interference, and where a peak interferes with a trough, they cancel each other out. We call this an interference pattern. To be clear, it's not the water molecules that are passing through these slits and creating this pattern. They're all just bobbing up and down. The waves of energy traveling through those molecules creates the interference pattern. Light creates the same sort of pattern when it passes through 2 slits. So for a long time, scientists figured it was just a wave. When they were confronted by the fact that light also behaves like a particle, they decided light has a dual wave particle nature. So if the little particles that make up an atom diffract and create interference patterns like a wave does, shouldn't we say all matter has a dual wave particle nature? Yeah. Now, you might be imagining these particles as if they were crazy little curveballs, but the wave-particle duality of matter is actually much stranger than that. If they were discrete little objects waving their way through these slits, shooting them one at a time would make them diffract, but it wouldn't create an interference pattern. Those only occur when you have 2 different wave patterns interfering with one another. But for some mysterious reason, shooting fundamental particles at a double slit one at a time still produces an interference pattern. It's almost as if each particle splits in 2, passes through the slits, and interferes with itself before hitting the screen. That is, except when you're paying attention? Wait, that can't be right. Really? As it turns out, when you place any sort of detector next to your double slit to see what your electrons are doing, they behave like particles and quit creating interference patterns. Which doesn't make any sense, but it's true. Anyway, that's it for this episode. You'll find more science and research opportunities for BYU undergrads in the description below.